Hello, my name is Daniel Hudson, and this is Lab 3 of Physics 1. For this experiment, I ran a computer model to calculate the net force acting on an orbiting star. I took a skeleton Python code, plugged in a few different equations to finalize the code, and calculated the elliptical path and the net force acting on a star all the way around that path. I then used that information to determine the mass of the black hole using the force of gravity equation. Some physics principles that were present in this lab. Well, the main one was the momentum principle, which states that the change in momentum over the change in time is equal to the net force acting on an object. I also used Newton's second law sum, which states that final velocity is equal to initial velocity plus net force over mass times the change in time. So some observations I made are that the arrows, which represent the net force acting on an object, or acting on the star as it travels its path, the arrows are significantly larger when the star is close to the black hole, which shows that the force of gravity pulling on the star is greater at that point. As a result, because the net force is larger, the change momentum is larger, so the star moves faster the closer it gets to the black hole. And we will see that in the computer model, which I will run in a minute. My calculated mass of the black hole was 8.06 times 10 to the 33 kilograms, and I will show how I got that here. Here is my Python code, which I used to run the experiment. As we can see, I entered in a few details down here, which was the star mass and the change in time, which is the number of seconds in a day. Down here is where I entered in some of the calculated quantities for our experiment, which is such as change of momentum, change of velocity, net force. Here you can see the momentum principle in action, net force equal to the change of momentum. I also calculated the parallel and perpendicular forces acting on the object, which I then used to create arrows detailing those forces when you run the code. Right here, I calculated the mass of the black hole by using the gravitational force of gravity equation, which is the gravitational constant times the two masses over the distance squared. The distance squared I just set equal to the star's position because I assumed that the black hole's position was the origin of our system. And here you can see when I run the program that as the star gets closer to the black hole, the arrows get much larger and it speeds up. And here as we go away, the star is clearly going much slower. The net force acting on the object is much smaller given the arrow size. And yes, that is the computer model. And so through the computer model, we were able to see the physics principles in action. I was able to calculate the force in the star by analyzing its motion starting from its velocity. I calculate change in velocity, calculate change in momentum, and then change in momentum over change in time, which I was able to say equal to net force, thanks to the momentum principle. And I was able to see how that then translates to parallel and perpendicular forces on the object, or on the star, specifically as it traveled through its elliptical path. I was also able to see how the force of gravity affects an object in space and how it changes as the object passes through its elliptical path and how it might move in different velocities at different times in its ellipse. So what does it mean? The question here is how are FNet and dPdt are related. As I've stated a few times, FNet and dPdt are equivalent mathematically due to the momentum principle. However, the way these two values are calculated is a little differently, since dPdt is calculated from the motion of the object itself, which is what I did in the Python code, where I calculated the change in velocity, change in momentum, and all that, while the net force is then the sum of the individual force vectors. And the reason these are equivalent is because the forces cause a change in motion, and the dPdt is that change in motion being carried out. So that's why they are equivalent. So the what if, could we just replace any black hole in there, regardless of mass, and keep the same force or keep the same motion of the star? This would be a resounding no, because a black hole of a new mass would change the force of gravity. Unless there is some other force change, which there isn't in our model, the net force would not be the same. Thus, the change in momentum over change in time would be different, and the object's velocity would be different as it rotates around the black hole.